Good day, everybody. How are you all doing? Hope you're doing great today. Today, we are going to talk about independence of chance events. By that, I mean, how do you know if two events are independent of each other? Okay. What is the technical way to find that out? Okay. What is the probability way to find that out? So, without further ado, let's get started by sharing the PowerPoints. Independence. Independent event definition. Two events E and F are independent if probability of E, as we explained before, that is the conditional line, given event F has occurred first. E given F. Notice what is happening on the other side of the equal to sign. It is just equal to probability of E. What does it mean really? It means the conditional probability of E given F has already occurred is not at all influenced by the fact that F has happened first, because the probability of E given F, conditional probability, is equal to probability of the individual event. So whether or not F happens does not matter in this case. Okay. If events E and F are not independent, they are dependent events. So probability of E given F is equal to probability of E, then E and F are independent events, because whether F or not, F happens or not will not influence the probability value of E. Vice versa, probability of F given E in that case is also equal to just the probability of F. So if there are independent events, now what exactly does independent event means? It means whether or not the other event happens, the second event happens, it will not influence the probability of the first event. So that's what we have written in the second one. Multiplication rule of two independent events. Okay. If the events E and F are independent, then probability of E and F happening, E and F happening, is probability of E multiplied by probability of F. This multiplication rule happens only if the two events are independent. Independent means each event is not influenced by the chance of other event happening. So probability of E given F for independent events is probability of E multiplied by probability of F. Okay. And now they extend it for multiple events. Previously, we were talking to E given F, E and F are independent. Here there are multiple events, E1 through E2 through EK. And if they're independent events, then the intersection and is product of all the individual probabilities. Okay, so here is an example. A new car has four critical components that all need to function properly in order for the car to work. The engine, the fuel system, the ignition system, and the cooling system. Suppose for a newly assembled car, E1 is the event that the engine functions properly, E2 is the event that the fuel system functions properly, E3 is the event that the ignition system functions properly, and E4 is the event that the cooling system functions properly. Suppose the four events are independent. Independent means whether one event happens or not will not influence the probability of the other event. So they have found out all these probabilities. You'll ask me, how did they find that out? And the empirical observations, that means they have observed these probability values over long periods of time. Okay, so E1 and probability of E1 and E2 are equal. They're equal to 0.98. Probability of E3 is 0.95 and probability of E4 is 0.99. So the probability that all of the function systems function properly is E1 intersection E2 intersection E3 intersection E4, E1 and E2 and E3 and E4. And because these events are independent, you multiply the individual probabilities. So probability that all the system functions function properly is 0.89, which is the product of the four probabilities of the four independent events. In the long run, 89% of the new cars would have all system functioning properly. So what is the suppose we want to find out that all systems except the engine will function properly. That means engine is not functioning properly. Probability of engine functioning properly is 0.98. So the opposite complement, even engine not functioning properly, is 0.02. That is the probability you take for the engine not functioning properly, the complement event, and then you multiply by the probabilities of other three events. Okay, and that is 0.018. That means in the long run, there is a 1.8% chance that the engine does not function properly and all other three systems function properly. Okay. So here they're talking about two types of sampling, with replacement and without replacement. So what is the big difference? The difference is sampling with, remember we're taking a sample from the population. Why do we do that? Because we cannot reach the entire population. It is too large, too big. So we select a sample from the population. Every time a member from the population is selected in the sample, we have two ways of doing it. Either we can take that individual from the population and do not replace him or her back in the population, that is sampling without replacement, or after selecting an individual from the population, we note the characteristics that we are trying to find out and replace the person back in the population. So the first one is that is sampling with replacement. Replacement means the individual selected in the sample goes back in the population for a second go around. Whereas in the second case, without replacement means the individual selected from the population does not go back to the population without replacement for the second go round. Okay. So what is the general rule of thumb? So that is the second paragraph. Uh, if we select a sample which is size n, small n, from a population of size capital N, then small n should be no larger than 5% of the population size. What do I mean by that? Suppose there are 10,000 students at your university. 5% of that will be 500. Okay, 10,000 students, 5% is 500. As long as your sample size is 500 selected randomly from the population of 10,000, you are fine. That is independent. Okay, in practice, independence can be assumed for the purpose of calculating probabilities as long as n small sample size is no larger than 5% of n. In my example, capital N is 10%, is 10,000 and small n is 500. I am fine because my small n is only 5% of the population. So the first paragraph says if a random sample of size n is selected from a population of size capital N, the probabilities of successive selections calculated on the basis of sampling with replacement and on the basis of sampling without replacement are nearly equal. So what does it really mean? So you are selecting a sample of size 500, in my example, from a population of 10,000. Whether you or not, you replace the person selected in the sample back in the population every time you're selecting somebody does not make a difference because the sample size is at most 5% of the population size. Okay, I will stop here today. Any question, any comment, write me a note. I'll respond back to you as soon as possible. If you liked my video, please give me a thumbs up. I appreciate that. If you like this video, share with your friends. And If you like this video, please subscribe to my channel by hitting the red subscribe button at the bottom right corner. In my channel, I have collected all these or presented, made a lot of presentations on explaining different topics, different subjects in math. So please take a look, please subscribe to my channel and take a look at these videos, might help you out. I appreciate the fact that you took time to watch my video. And please do not forget to watch me tomorrow. I'll be back again tomorrow. Thanks for watching. Take care. Have a nice day. See you tomorrow.